Okay.
So our first speaker is Ilya.
All right. Thank you very much. I apologize in advance if I have to cough profusely during this talk, but it seems that Jerusalem is a place that sort of gets under your skin in more ways than one. So thanks to everybody who managed to brave the hangover and still show up today. I will try to talk about the tidal disruption of binary stars, and this is work that was largely done with Yuri Levin from Monash, and now there is a graduate student from Birmingham, Ben Bradnick, who has also become involved in the second phase of this work. This is not the plot that was supposed to come out. Okay, wonderful. So here we have a nice binary. So this is Yuri at the top and me below, and we're trying to, be a nice, happy binary, sort of dance around each other. But there's a little bit of a problem here because Yuri, from what I hear, is a terrific tango dancer, and the only thing I can dance is salsa, and rather than being terrific, I'm pretty much terrible at it. So that means that as we are dancing our happy dance as a binary, we really, we can't really stay in the same place. We keep on bumping into things, as bad dancers tend to do in a dance floor. So we bump into other stars, into other binaries. Sometimes we bump into maybe some molecular cloud, or we bump into an intermediate mass black hole, or something else. And that, of course, means that we're constantly changing our energy and, in particular, angular momentum, as Tal has told us yesterday. And that means that pretty soon we find that instead of just dancing somewhere far away from any danger zone, well outside of certainly the sphere of influence of any black holes, we find ourselves getting a little dangerously close to a mean black hole over there. And of course, you know what happens next. The standard picture is that we get tidally separated by the tidal forces of this black hole. Perhaps I get captured by the black hole, get stretched, eventually tidally disrupted, and fall in. Perhaps Yuri is a little bit more lucky than me and is instead ejected as a hypervelocity star, going off at several hundred kilometers per second or more. Okay, that's the standard picture.
You don't get ejected, you don't get pulled by the black hole so quickly. I mean, you just get captured.
Sure, you get captured, right? And eventually, if you may continue to walk around in angular momentum space, and eventually you right, indeed. So first you're just in the loss cone for binary tidal separation, and then perhaps you make your way into the loss cone for individual stellar disruption. Absolutely, the difference is that essentially, it's a question of the size of the binary versus the size of the star that determines which loss cone you're in. Absolutely, Tom. But consider the following situation. What happens if we are really quite far away? As I said, perhaps starting out at a radius beyond the sphere of influence of the black hole. And then we are certainly very much in the full loss cone regime, meaning that a single unlucky perturbation to our orbit somewhere at apoapsis very far away, where we spend most of our time and where we have such a huge lever arm because we're on such a large period, eccentric, nearly parabolic orbit around the massive black hole, that a little perturbation out there can really very significantly change the closest approach that we have to the massive black hole. We're scattered directly into the loss cone for not just the binary tidal separation, which is denoted here by the dashed blue lines, but for the tidal disruption of individual stars. So you might say, well, this is surely extremely unlikely, but not necessarily so unlikely, because if you actually consider, for example, the fact that it seems that Opic's law more or less holds, and binary radii roughly look like they're uniform in the log, and for massive stars, if anything, they look like they're more concentrated at small separations. We actually have a non-negligible fraction of binaries which have radii that are only a few times larger than the stellar radii, right? Where the stars are not so far away from Roche lobe overflow. And certainly for those things, there isn't a huge difference. It's maybe an order of magnitude, maybe less, in the size of the loss cone for the tidal disruption of a star and the tidal separation of a binary. So suppose we're scattered over here directly into this loss cone for the tidal disruption of a star. So what happens then? Well, what happens then is that, of course, we're still initially tidally separated. That happens first. But then we essentially follow almost the same trajectory because the angular momentum that the center of mass of our binary has around the massive black hole is still significantly larger than the relative angular momentum we have as relative to each other as part of a binary. And so now Yuri and I find that really, yes, we're tidally separated, but then we follow nearly the same trajectory around the black hole. And so we're now going to be sequentially tidally disrupted. One of us gets tidally disrupted first, the other one follows shortly thereafter. So now we have a possibility for a double tidal disruption event. Okay, I said that this is not so incredibly unlikely. We actually did some numerical calculations using Hannah Rain's rebound package, basically just integrating the trajectories of binaries drawn from some reasonable distributions of initial orbital separations, initial masses and mass ratios, initial eccentricities, and evolved them as they were perturbed and in some cases ended up coming too dangerously close for their own good to the tidal disruption loss cone. And we indeed found that a non-negligible fraction of these binaries ended up having double tidal disruption events. So here there are a couple of histograms, one as a function of the periapsis of the binary's center of mass relative to the massive black hole in units of solar radii, and you can see that when the binary comes too close to the massive black hole, double tidal disruptions are overwhelmingly favored. Of course, if the binary stays happily far away from the massive black hole, then usually this is what we call an uneventful encounter. In blue, nothing much happens. There are a few cases of single tidal disruptions, this light blue color in the intermediate regime, so it can happen, of course, because, for example, even though our stars may follow a fairly similar trajectory, but suppose that our stars have very different masses and therefore different radii, it can happen that one of the stars gets tidally disrupted and the other one doesn't. Also, there are some possibilities for tidally induced mergers, and I'll discuss those in more detail later. Also, here's a plot showing what the behavior is as a function of the same major axis of the binary, and again, as you might expect, smaller semi-major axes generally prefer these double tidal disruption events. They're less likely as you go to larger semi-major axes.
These fractions can be estimated analytically. In the full loss cone case, it will be roughly the ratio between the separation of the two stars to the radii.
Exactly. Exactly.
And in the empty loss cone, it turns out to be not so different from that. It's just a logarithmic correction. This is somewhat of a surprise because you would think that in the empty loss cone things diffuse and they only hit the tidal radius from the outside. But strong scattering can actually bring them also deep into the tidal radius and bring the result which is not that different from the empty loss cone.
So the next question you might ask is, could we actually have any hope of, if there is really a double tidal disruption, of being able to tell whether or not this is somehow different from just a single star being disrupted. Is there any hope of having a special signature here? And let me say up front that we have not done any hydro simulations. I'm in fact very much hoping that somebody would become interested in doing one. But all we have looked at was just the mass return rates, m dot, without considering anything about the interaction of the tidal streams either with themselves or with each other. But you might just simply ask yourself the question, what is the sort of typical separation between, let's say, the peak times for the mass return rates, or they're sort of the presumed peak of the luminosity as estimated using this very simple prescription saying that luminosity is just directly proportional to m dot. And we find that in general, the separation can be, at least in some cases, of order the typical size of the peak itself, and that the in most cases because the stars are roughly of comparable size in a significant fraction of the cases, we're using essentially a uniform in the mass ratio initial distribution. It means that the mass return rates are also likely to be fairly comparable, so the two peaks are going to be of a comparable size. So just to give you a little illustration, here is what using the prescriptions from James's work, here is what the behavior might look like just adding together completely independently two peaks from the tidal disruption of one star from the tidal disruption of another star. In this case, actually, it's not so much the difference in the tidal disruption times that matters as the difference in, just due to the size of the differences in sizes of the two stars, the difference in the time between nominal tidal disruption, the time when you get to the tidal disruption radius, and the peak of the mass return rate, basically the time when the most bound ejecta make it back. And you can see that, okay, this is a 10 to the 6 solar mass black hole. There's a difference of order of a month. In this case, of course, it would be a much larger difference for more massive objects.
You're assuming that this figure that these are two completely independent events.
Exactly. And this is clearly not the right thing to do. Here's a little visualization. This one is actually courtesy of James. So I passed on a couple of our dynamics simulations to James, and he plotted what he thinks the ejected streams would look like. And you can see that in some cases the ejected streams essentially are non-interacting. So you can see this here. This is a sort of 2D plot in the orbital plane. This is a 3D plot, but with one of the axes artificially enlarged to make things more visible. But in this case, you can see that there is clearly interaction and self-intersection of the two streams, and this happens even before you get you return to periapsis. So in other words, there's going to be a lot more interaction going on here, and this could, of course, very significantly change the potential circularization timescale, could very significantly change the overall light curves that you might expect to see from this kind of an event. So Rem, I completely agree with you that the right thing to do would be to in fact try to model what happens using, let's say, some sort of an SPH simulation, what happens with the interactions of the streams. One thing to keep in mind is that usually, precisely because the angular momentum around the massive black hole is more significant than the delta L due to the orbital angular momentum of the two stars around each other, we find that typically the orbital planes of the two ejector streams are going to be very similar, and even the eccentricity vectors are going to be very similar, right? You can see this over here. You can see that there's a little bit of a difference between eccentricity vectors here, but really not much. in both cases. So the eccentricity vectors are typically aligned, and I think in only one out of 1,000 simulations that we had done did we see a case where the orbital planes were very significantly different from each other, misaligned by more than 90 degrees, right? In most cases, the orbital planes are a few degrees away from each other. The eccentricity vectors are a few degrees away from each other. So that means it's not going to be a case of something completely wild happening, but absolutely there's going to be some interesting stuff going on here, and I think it would be very interesting to look at this in more detail.
I actually have a very, I didn't think of this before this hearing you talking about it, but I have a very different picture in my mind of what's going to happen. I don't think it's going to look like this for a typical case, because I think if the separation between the two stars is somewhat larger than their own sizes,
Yes.
has to be, then one of the tidal springs is going to be completely unbound. It's going to be tidally disrupted, but all the material is going to be unbound, because the spread in the energy within the star is going to be smaller than the spread in the energy between the two stars. And the other one is going to be something like this. So one of the debris, I think, is never going to, from one of the stars, is never going to return. All of it is going to be lost in a typical case. And the other one, all of it is going to be a free.
Sorry, I don't understand this argument. So I don't understand why, by the time the two stars are, we're talking about the stars being tidally disrupted, right? The binary has been tidally separated. The stars don't know about each other and don't care about each other, right?
But
So
they each differ from the parabolic orbit, the nominal parabolic orbit that they both came on, by a significant amount, which is comparable to their separation, not to their size. So one of them is going to have overall a positive energy, and one of them is going to have overall a negative energy, like the hypervelocity star separation. One of them is going to be bound, the other one is going to be ejected as a hypervelocity star. Now, because both of them came very close to the black hole, both of them are going to be disrupted. So the one that should have been disrupted was a point mass, a bound object, will be one of your ellipses plotted in here. And the other one that should have come as a hypervelocity star would be a disrupted hypervelocity star, but none of its material is going to come back.
So I don't think that actually happens. It may happen in some small fraction of the cases. I don't think it happens regularly, but let me actually check on that. Okay, that's a very good suggestion. Let me check on that.
Will actually happen in the majority of cases, but I was thinking about this when I cleared this before, that it's only in the phase of the velocities
Right.
perpendicular.
What I'm
to that,
suggesting will happen in the middle of the
the
case.
ring
That's what I
in
think.
general.
It's not entirely unbound, but the spread in energy is only 8,000 kilometers per second from the most bound to least bound debris. The typical hypervelocity star velocities are 2,000 to 2,000 kilometers per second. So at most, you'll have a larger unbound fraction, but you'll still have some bound debris in both double tidal
I don't see
velocities.
how this would be, because the spread in energy is proportional to the separation. The separation within the star is proportional to its radius, and between the star proportional to the separation between the stars.
It's not, it said at the tidal radius of the thing that you're destroying by tide, right? So for the binary, you cross the tidal radius first. The stars cross their tidal radii deeper in.
Yeah.
So it's a deep plunging encounter, so the binary is actually tidally destroyed before the stars are. The only time it would be similar is when they're a contact binary.
Yeah.
So that's why the energy spread across the binary is smaller than the energy spread across the individual stars.
Ram, consider an extreme case. Suppose I took my binary and I tossed it at the massive black hole so that the center of mass of the binary was going straight into the massive black hole, right?
Yes.
Right? Then, okay, clearly, whatever little perturbation I have on top of this, right, from the binary moving around each other, both stars are going to be, obviously, will end up being tidally disrupted, right? And they will both be fully bound, right? So I don't think.
No. Suppose there are 2 point masses which you throw readily into the black hole. When they come out, one will be a hypervelocity star and the other one will be bound. They can't be both bound because then you'll have negative energy.
The center of mass orbit hits your
Yes.
Right? And now it's the question of the spread of the energy compared to the mean energy of each of these objects, which is the question James tried to address, but I'm not sure his conclusion is right. Okay, I don't want to.
Okay. Yeah. Let me think about this. Okay, that's a very good point. Let me think about this. Thank you. Okay, so I just wanted to say that maybe there are some unusual tidal disruptions, just to provide a little bit of a justification for this. I'm not saying that this is necessarily that these are indications that what we are proposing here is really happening. So here is a recent result from Merloni et al. And maybe that you see something that looks like a sort of t to the minus 5/3, roughly speaking, fall off, but with a second peak over here, just maybe. This one is actually from work by Group 8 also. This is work that Stephanie and Richard had done, and I think Stephanie had already mentioned this event during her talk. So this is a situation where something like 20 years later you had a second transient event coming from the same system that was initially identified as a X-ray tidal disruption source. Now, one of the possibilities here is that, for example, if this is what we identify as single tidal disruptions, in some cases, of course, in practice, the orbit is not exactly parabolic, and what can actually happen is that the second star does eventually return, but returns on a orbit which is brings it back towards the massive black hole, something like on average 10 to 50 years later, and so these are the kinds of events that we might be potentially seeing if there's a single tidal disruption of a binary, but followed by the tidal disruption of the other companion. The other interesting possibility, of course, is what does this say about the famous jetted tidal disruptions, like this famous event that we've heard so much about from Swift. And of course, one of the interesting possibilities here is what about the systems that actually got merged by tidal forces? The binaries got merged just prior to possibly tidally disrupting the merger product. So here, of course, one of the big questions is how do you get sufficiently large magnetic fields or magnetic fluxes in order to power prompt jet formation. And for Sashikov and colleagues, for example, argued that you need a magnetic flux of something like 10 to the 29 Gauss centimeter squared in order to power this prompt jet formation. So where do you get such a big magnetic flux from? And one of the possibilities maybe is, and I know that there are people who disagree with this in the audience, but one of the possibilities may be that if you actually have a binary merger, then as a result of this binary merger, you end up possibly enhancing the magnetic field in the remnant by essentially winding up the magnetic fields in the process of the merger. And so you may have a star with a very significantly enhanced magnetic field, and maybe when you tidally disrupt that merger product, you now have a much greater reservoir of magnetic field or magnetic flux to power prompt jet formation. And let me just mention one last thing. I realize I'm basically at the end of the time. Is this was all about the full loss cone events. What happens in the empty loss cone? And the answer is that in the empty loss cone you actually have. I'm going to skip a couple of slides, but you have quite a. This is work that we're doing right now with Ben Bradnick, as a Birmingham grad student, and we see that and these are very preliminary results, but we see that there are quite a few tidally induced mergers that happen in the empty loss cone regime, and of course some of these objects will go on to be tidally disrupted again, so it may be that quite a non-negligible fraction of overall tidal disruption events are in fact tidal disruptions of fairly recent merger products. Okay, and given that I'm at the end of my time, I'll just post these conclusions and stop here. Thank you.
That's a comment on the mergers. To check whether you get much more of them in case we start using client binaries. Because we saw in papers with Fabio Antonini that you could actually get these mergers because of Kozai during the info. So just check it. I would suspect that many of the mergers are those with highly inclined.
So we are doing simulations at all inclinations. I don't have actually a plot as a function of inclination, but you're absolutely right that inclination plays a big role. So one thing that you can, sorry, I'm going to show the two slides I skipped in response to Hagai's talk, so Hagai's question. So here we're just considering actually there's no evolution here of the binary's angular momentum in this particular, in the next two plots, the binary's angular momentum relative to the massive black hole. All that we're doing is we're just launching the binary multiple times on the same parabolic orbit with a periapsis separation of something like 4 times the binary's tidal separation radius, right? And as you might expect, if you look at the same major axis or you look at the eccentricity, there are little fluctuations. This is the point where the binary happens to fly right by the massive black hole. Then we just compress the part when the binary is very far away, right? This is, okay, I call it parabolic. Suppose it's an orbit with an eccentricity of 0.9999, right? So just so I don't have to continue to calculate the trajectory when nothing is happening, I'm just gluing the passages onto each other, and you see that, okay, nothing much is happening. There's a little bit of oscillatory behavior at a level of 1 over the periapsis divided by tidal separation cubed, but no secular growth. And then in some cases, you see things like this, and indeed inclination has something to do with it, but it's not just inclination. But you see that over here, yes, these are the passages where we fly by the massive black hole, but you see that, for example, for eccentricity, right, we see something that looks like actually, something almost like secular evolution, even though these are just independent flybys. And you can see, for example, over here, eccentricity has gone up from 0.92 to basically nearly 1. So this means that a merger is extremely likely at this point, for example. This is the eccentricity of the inner binary, just to be clear. Rem?
I think I'm taking my comment back, because I think indeed the larger the separation is, the smaller the spread in the energy, and therefore the spread in the energy within each star is going to be larger. So I think that figure is not accurate because you don't show the unbound stuff, and there must be some of it, those 2 rings. Right.
Oh yeah, okay.
So the unbound
Yes.
stuff is missing.
Yes, there is no unbound stuff in that, right?
But
absolutely.
That